the centripetal acceleration. Now here it's also possible to argue using these different Reynolds stresses to sort of get the same solution that we found, or not solution, but the same image. You will have an unstable side and you have a stable side. One side enhancing the turbulence, another one suppressing it. But I would say this argument you have to read through here, not so easy to understand. Looking at the different production terms and see, okay, the ratio here of the different Reynolds stresses, which one is produced when you have one of them, then he will produce one of the others, and so on. Not so easy to see the logic here. Also, who is the chicken and who is the egg? Not so easy to see primary, secondary effects here. So possible, but I would say easier just to jump directly to the conclusion. The turbulence is not isotropic. Okay, K epsilon, K omega, two equation models will have problems. Much easier. The rotational effect, sort of the same there as well. Let's see if we have a figure, which we should be in the back here somewhere. The figures are located in the end here. It's a little sad. So here you have a typical velocity profile then in a slightly curved channel. More laminar-like velocity profile here on the suction side, and then more and more turbulent shoulder here on the pressure side. When it comes to turbulence, no sorry, rotation, should be here somewhere. No, I missed it. Here we go. You have a straight channel, it's not curved at all, but you set up a system rotation. The coordinate system now, x, y, and z, goes out, then you have a positive rotation against the clock. So when you start to move this channel, of course, high pressure here, and then low pressure on the other side. Hence, this drawing is wrong. It should be flipped. So on the suction side, you will have low pressure. You should have a more laminar-like profile. And on the pressure side, sharp, more turbulent-like profile. So, but you can use the same argument here as we had with the curved channel flow. So we have a straight channel, and then we rotate actually around any point. Doesn't really matter where that point is. You will then have the equation system, and typically what you do here, you will set up a coordinate system and then be a part of the rotation. You don't use an absolute coordinate system, you use a relative. So now the equation of motion should read something like this. ddt of the velocity vector equals, and then all of these forces, pressure, you can have gravity, you can have viscosity, like this. And then you have to adjust Newton's second law of motion because you are not in an inertial frame anymore. You take one acceleration that actually belonged to the left here and put it on the right hand side, reading 2 times, and that should now be omega times omega cross the relative velocity. So here you'll have the rotational vector going in this direction. So the Coriolis acceleration now will be negative on this side. So you have an sort of an apparent force, an additional force in your problem. Of course, it's not a force, it belongs on the other side as an acceleration, but this is what you will do. So when you have a flow going in this direction, what will be the direction of this additional apparent force? Well, the omega, he goes in this direction. The relative velocity goes like this. Okay, so omega cross v relative should go up. Negative, go down. So you will have a force in the downward direction. And of course, that means it will be high pressure down here. You will get a pressure gradient, say dp dy, to balance this apparent force. So, no, that was the other way around, of course. Higher pressure down to get this motion at all. So now if we sort of do the same with looking at one element moving with one velocity, and then it should be a balance between the Coriolis force and this pressure gradient that has been set up due to the rotation. And then somebody kick you upstairs. Okay, you will be faster than your surroundings. Now, this turn will be bigger for you. So bigger than this pressure gradient, and there you should be pushed down again. Bigger, yeah, because you have a minus sign, I guess. So you should be pushed down again. Let's see if this works. If we are here and then pushed up, you will be faster, then he will be bigger than your surrounding, then you should continue this way. So it should be possible here as well to get the same stable, unstable side, just due to rotation, or system rotation. So again, if you are planning to simulate something like this using a two equation model, you are in danger, because you can't really tell the difference here between those two sides. You won't see it at all, and you will get the same solution on both sides. Of course, rotation, yes, it's possible to add this effect. So you have a special version of K epsilon, which then should be able to handle this at least better. But just be aware that if you are in such a rotating world, you should or must pay extra attention to it. bit about these different results here that are plotted. So here we are talking about the Stanton number, something to do with the heat transfer along a wall. So you checked a straight wall, a convex wall, and concave wall, and then you see really a strong, very strong curvature effect, even with quite weakly curved surfaces. So the effect is there, oh yes. These are not so interesting, are they? The law of the wall, a lot of experiments here, quite clearly strong differences whether you are on the convex or the concave wall. For the rotating channels, I think here we have a rotating channel, case A. You don't have any rotation at all. So the measurements here, the velocity profile, very turbulent indeed. Sharp shoulder and then flat center part. And not much change when you go further downstream. And this one, here clearly you see the shoulder getting more and more sharp. This sharp distance closer and closer to the wall, you increase the turbulence. So clearly here you will have the pressure side, the unstable side, more and more turbulence. On the other side, you see the velocity will increase, run faster and faster, and become more and more laminar-like. It's much cheaper to push a laminar flow through a pipe and a channel than a turbulent. So the velocity will go up. And here the same, looking into the turbulent streamwise intensity. And what do we mean about streamwise intensity? Intensity, then you are talking the component that makes the turbulent kinetic energy, K. So he consists of U flux square plus V flux square plus W flux square. So the streamwise, if the streamwise is in the x direction, so then the streamwise turbulence intensity, that will be the U flux alone. And if you don't have any rotation, he will typically peak very close to the wall. Very close to the wall, that's where the action is going on. That's where you produce the turbulence. So very close to the wall, you will have the maximum of your turbulent kinetic energy, and then he will be damped down in the center of your channel. With the pressure side, and this peak should move closer and closer to the wall, and also should increase in magnitude, while on the suction side, stable side, he should tend towards zero, become a laminar flow. Now here, it's a sort of interesting one with a rotating in a rotating channel. They measured the wall shear stress on each wall. So without any rotation, you have the same wall shear stress, of course, symmetric. But then when you start to rotate, on the turbulent side, the unstable side, the wall shear stress is going to increase more and more. And on the stable side, it will drop. And these measuring points here, they had been sort of a question for several people for several years. The measurements here were done by Johnston in the 70s. So actually we talked to the guy, and he had to admit that these points had a very high degree of insecurity, so you shouldn't really believe them. And the reason also you shouldn't believe them is if you look at the global force here, you have a channel, you set up a pressure difference as a driving force, then you know the total force acting on the entire domain inside your two plates. And that force has to balance the sum of these two forces. Then all of a sudden, one of the forces can't all of a sudden drop. If this really should drop this much, then he has to increase similarly to have a force balance. So they are not correct. And he have to admit that himself that no, they shouldn't believe these measuring points here. But this differences in wall shear stress, that one is actually absolutely believable. This is something also that especially K epsilon is not too happy about. You have the backward facing step, so you have one big primary vortex. You can have some secondary vortices here, and if you can zoom into the corner, you can have several secondary vortices. And typically what we will be interested in here is finding the reattachment length. So this is one of the exercises I gave to my students with open foam. Find the reattachment length, and then using, for instance, K epsilon. And playing around with the mesh, you can have a reattachment length from, say, 1 step height to, I think, 20 step heights. You can get any answer you like, just change the mesh a little bit. With DNS and laboratory experiments, should be 6.5, 7 step heights downstream, but very hard to get correctly. And with K epsilon, this was really just funny. Of course, if you're interested in a correct solution, it's not so fun anymore, because you can get any solution, you just change the mesh a little bit. So it's a very bad model for this problem. Yeah, some different predictions here. Now here compared, let's see, that is the and ASM and BVM, yeah. I think here the BVM, that should be in the full stress. I think here you compare the algebraic stress model with a full Reynolds stress model. And what you compare here are different Reynolds stresses. Here the shear stress, UV, scaled by U1 square. And here you have the total K with the same scaling. The total K, okay, the two models have at least a similar behavior, but for the shear, there's definitely some differences between them. Of course, here you can't even start talking about the K epsilon or something. He can't find this shear stress whatsoever, so no way. But these are sort of second order moments. Always harder to find second, third, fourth order than just one intensity. Okay, that was the end of the first turbulence part. The second one then will contain some articles, which then more or less will be examples how to look at complex problems where we know the classical two equation models will fail. So as I said, we will have 3 of those. And then finally, we will start looking a little bit into large eddy and DNS at the end. But that will then be the topic on next Tuesday. Also, I'll give you another article, a little bit concerning how we start a DNS. Because that's also a chapter of its own. But then we should be finished with Turbulence on Tuesday. I don't need more than 2 hours, and hardly that, I think, to cover then the final part of Turbulence. And then on Wednesday we will then start with OpenFOAM. Now remember, OpenFOAM is not mandatory. I want to ask you anything about it on the exam. But if you want, if you're curious about what is OpenFOAM, then come and join us and play around with it. And bring an old laptop, Windows or Linux, if you find one. I mean, if you don't have one, steal one from a friend or something, you find it. It's not fun to just sit and listen. I expect you to have a computer so you can run yourself. Because the first time you touch OpenFOAM, that's not so easy. It's a little messy. But if you look at the price, it's very good actually. It doesn't cost anything. Any questions from you? Then we can take an early dinner. We stop.